so we've defined the notion of a vector, we've defined the notion of a matrix, we've discussed some of the basic operations we can perform on vectors and matrices, and now I want to sort of bring this all together to talk about perhaps the most important concept we'll cover in the course. At least everything else we do in the course will almost always somehow come back to this. And this is the notion of a linear combination of vectors. So, by definition, a linear combination of vectors is any expression that looks like this. So we're looking for expressions where we take a bunch of vectors. In this case, the vectors are v1, v2, up to vn. We scale them by any numbers we want. So we scale the first vector by any number we want, called c1 here. We scale the second vector by any number we want, called c2 here. And we keep doing this until we get to the last vector. So we're scaling a bunch of vectors by a bunch of numbers, and then we add everything up. This is the notion of a linear combination. And this is one of the most important concepts in mathematics. It's shocking how many concepts in mathematics end up boiling down to taking a linear combination of things you're interested in. So here's maybe our first example of a linear combination. Here what we have is a linear combination of three vectors. So the three vectors that are listed to the left of this equal sign in this equation are the vector 1, -1, 0, 2, and 2, -4. The idea here is that I'm scaling these vectors by numbers that I randomly chose. I actually wrote a program that just randomly chose three different scalars to scale my vectors by, and those scalars ended up being -3, 4, and 2. So now I'm going to scale 1, -1 by the number -3. I'm going to scale 0, 2 by the number 4. And I'm going to scale 2, -4 by the number 2. And when I do all those scalings and then I add everything up, I produce this new vector, 1, 3. So the language we would use as mathematicians here is we would stare at this equation and we would say, okay, we've managed to produce the vector 1, 3 by taking a linear combination of 1, -1, 0, 2, and 2, -4, using these particular scalars. So we would say that the vector 1, 3, again, here we're using this transpose notation to more efficiently use our vertical space. We would say the vector 1, 3 is a linear combination of these three vectors, 1, -1, 0, 2, and 2, -4. So to take a linear combination of vectors means to take some list of vectors you're interested in, multiply them all by any numbers you want, and then add all those things up. Now here's just an example playing around with this idea. So let's say that the vectors we happen to be interested in are 2, 0, -3 and -1, 0, 5. So let's say we're just working on a problem and those are the two vectors we're interested in. Well, what would a generic linear combination of these vectors look like? Well, by generic, what I mean is, like, what could we possibly produce by taking a linear combination? So the idea here is, well, let's say we scaled this first vector, 2, 0, -3, by any number we wanted. Call that number C1. And then let's say we took the second vector, -1, 0, 5, and scaled by any other number we wanted, C2. Well, when we do those scalings and add everything up, we produce this new vector. And this new vector has three coordinates. The first coordinate is 2 times C1. C1 is that choice of the first scalar we chose, minus C2, which is the second scalar we chose. The second thing to notice is that the second coordinate is always equal to 0, because C1 times 0 plus C2 times 0 is equal to 0. And the third coordinate is always equal to -3 times C1 plus 5 times C2. So one thing that pops out of this is by taking a generic linear combination of these two particular vectors, we always produce a vector that has 0 as the second coordinate. Now this might not seem interesting, but there are things you can conclude from it. For example, you can never achieve the vector 7, -8, 4 by taking a linear combination of these two particular vectors. And the reason is because taking any linear combination of the two vectors we started with always produces a vector with 0 in the second coordinate, but this vector, 7, -8, 4, has a -8 in the second coordinate, which is not equal to 0. So 7, -8, 4 can never be expressed as a linear combination of the two original vectors we chose. So if we wanted to just start with these two particular vectors and then take linear combinations, we will produce all sorts of new vectors, but we'll never produce 7, negative 8, 4, for example. So we're sort of missing out on lots of vectors by only taking linear combinations of these two particular vectors. And this is an incredibly common situation in math. A lot of problems sort of boil down to that idea. So a lot of problems fit into this archetype. Can we take a linear combination of vectors that we're interested in, so v1, v2 up to vn here. So if we start with v1, v2 up to vn and scale by any numbers we want and then add everything up, is it possible to produce some other vector b that someone has given us? And the next step here is, well, since this is such a common thing in math, it would be nice if we had maybe language that was more efficient to set this sort of equation up. And this is the idea behind a matrix vector product. Okay, so what is a matrix vector product? Before, we saw how to take a vector and scale by a number. We saw how to take a matrix and scale by a number. And we saw how to add matrices and vectors. Now we're combining a matrix with a vector and we're multiplying them together. So how does this work? So here's what we need in order to take a matrix and multiply by a vector. I need my matrix to have any number of rows I want with n columns, and n needs to be the same thing as the number of coordinates inside of the vector v. Okay, so what does this mean? This means that whatever matrix we're working with, we need the number of columns, which I'm writing here as vector a1, vector a2, up to vector an. I need that number of columns to be the same as the number of coordinates inside of the vector that I'm interested in multiplying my matrix by. If this condition is not met, then the multiplication will not make sense. So what do we do if the condition is met? By definition, the matrix vector product, A multiplied by V, is the linear combination of the columns of A where the scalars that we choose are the coordinates in V. So let's go through this equation. To take A and multiply by V means that we take a linear combination of the columns of A where the scalars we use in the linear combination are the coordinates inside of V. So A times V can be found by taking the first scalar inside of the vector V and multiplying by the first column of A. Then we take the second scalar inside of the vector V and multiply by the second column of A. And we keep doing this until we get to the last scalar in V, where we multiply by the last column of A, and then we add everything up. So to take a matrix vector product is to take a linear combination of the columns of A, where the scalars we use to build the linear combination come from the vector V. And one thing to point out here is that if A is an m by n matrix, each column of A is a vector in Rm, which is the number of rows. And when we take a linear combination of those vectors, of those columns, we produce a new vector in Rn. So in order to take A and multiply by V, we need the number of coordinates in V to match the number of columns of A. And when we perform the matrix vector product, we produce a new vector that lives in R to the number of rows. Okay, so this is a lot of math symbols. So let's see this concretely in an actual example. So here we have an example where we are taking a matrix and multiplying by a vector. So the matrix we're working with is this matrix here. This is a 4 by 3 matrix, which means we can only multiply this 4 by 3 matrix by vectors that have the same number of entries as this matrix does columns. Well, this matrix is 4 by 3, meaning it has 3 columns, so we can only multiply by vectors with 3 entries in them. Now, this matrix and this vector fit the criteria, so how does the actual matrix vector product work? Well, we're supposed to take a linear combination of the columns of the matrix using the scalars inside of the vector in the linear combination. So how can we do this actually? Well, the first thing we're going to do in this matrix vector product is we're going to pluck out the first coordinate of the vector and use that to scale the first column of the matrix. So that's exactly in our first expression here in our equation. So we're going to take -1, which is the first coordinate of the vector, and multiply by the first column of our matrix, which is 6, -5, -7, -3. Good. So that's the first expression in the equation, but there's two others. In the next term in our sum here, we're looking at the second scalar inside of the vector we're multiplying by, and using that to scale the second column of our matrix. So the second term in this sum is 7 multiplied by the vector -2, -1, 4, 1. So that's right here. And finally, to complete this matrix vector product, we use our third term, which is obtained by taking the third coordinate inside of our vector and scaling by the third column of our matrix and tack that onto our sum. So the last term in our sum here is 2, which is the third coordinate of the vector, multiplied by the vector 2, 0, -4, 3, which is the third column of our matrix. So we take this matrix, we multiply by this vector. The way we do this mechanically is by plucking out the coefficients inside of the vector we're multiplying by, using those to scale the columns of the matrix, and adding everything up. One thing I'll point out is I haven't completed the addition here, but if you do that yourself, what you'll find is that after taking this 4×3 matrix and multiplying by this vector in R3, we produce a new vector that's in R4. This goes the other way too. So in this previous example, we started with a matrix vector product, and we walked through the mechanics of actually multiplying this out to produce a new vector. This is useful in the other direction too. Sometimes it's the case that we encounter a linear combination in some problem, and it becomes useful to rewrite that linear combination as a matrix times a vector. So here, the idea is that we're starting on the left-hand side of this equation, and for whatever reason, we're working on a problem, and the expression -5 times this first vector plus 2 times this second vector pops up. Well, we recognize this as a linear combination of two vectors, which means we can rewrite this expression as a matrix multiplied by a vector. The first term in this linear combination is -5 multiplied by the vector 1, -7, 1, 3, 1. So if we're going to write this as a matrix vector product, we could extract the first vector in this term and put that into the first column of a matrix, and then we can build the vector that we're multiplying by taking this -5 and putting it as the first coordinate of the vector we multiply by. So that's the first column of our matrix, and that's the first scalar of the vector we're multiplying by. Now let's move to the second term here. The second term is 2 multiplied by the vector 4, 0, -1, 1, 1. This becomes the second column of our matrix and the second coordinate of the vector we multiply by. So the second column of our matrix that we're building here becomes 4, 0, -1, 1, 1. And then the second coordinate of the vector we're multiplying this matrix by is 2, because that's the scalar we used in our linear combination. So that's the mechanics of taking this linear combination to the left-hand side of this equal sign and rewriting it as matrix times vector. And this is actually useful. The way I like to think of it is we took something that looks kind of ugly mathematically, a scalar times a vector plus a scalar times another vector, and we've elegantly rewritten this expression as just one thing, a matrix A multiplied by a vector V. So this turns out to be an incredibly powerful idea in linear algebra. So the sooner we understand these mechanics, the quicker we can do more interesting things with matrices and vectors. Now, again, there's a word of warning, because it only makes sense to take a matrix and multiply by a vector if the number of coordinates inside of that vector matches the number of columns of the matrix. So here we have sort of two shapes that we might try to multiply together. Let's talk out whether or not these make sense. On the left over here, we're taking a 4 by 2 matrix, and we're attempting to multiply this by a vector in R4. Well, this matrix has 4 rows, but it only has 2 columns. And in order to take a matrix and multiply it by a vector, the number of coordinates inside the vector must match the number of columns of the matrix. So this expression here actually makes no sense. This is not a defined product, the way that we've set things up. On the right over here, we have a different example. Here we have a 3 by 3 matrix. So this matrix would generically have 3 rows and 3 columns. What would happen if we attempted to multiply by a vector with only 2 entries? Well, this wouldn't work either, because in order to take a matrix and multiply it by a vector, the number of coordinates inside of the vector must match the number of columns of the matrix. Here the number of columns is 2, and here the number of coordinates inside of the vector we're attempting to multiply by is 2. So sorry, the number of columns of the matrix is 3, and the number of coordinates inside of the vector is 2. Those numbers don't match, so we can't multiply them together. So neither one of these expressions makes sense, because the number of coordinates inside of the vector we're attempting to multiply by does not match the number of columns of the matrix that we're using. Okay, so I want to summarize this idea of matrix vector products in a concise, elegant mathematical way. One way to view matrices is as data storage. If you just have a bunch of numbers that you want to organize into rows and columns, matrices are the tool for the job. But we have another perspective that's emerged here by studying the idea of a matrix vector product. Instead of viewing matrices as data storage, we can view them as machines of a sort that have inputs and outputs. So this perspective tells us that matrices translate vector inputs into vector outputs. And all of that is summarized in one elegant equation. A times a vector x equals a vector b. This is an equation that's going to pop up again, again, and again throughout the course. So when we write A times a vector x equals vector b, what are we actually using here? Well, A needs to be a matrix with m rows and n columns. And remember, in order to take a matrix and multiply by a vector, the number of coordinates inside of the vector must be the same thing as the number of columns of the matrix. So when we write ax equals b, we're implicitly stating that x belongs to Rn if A has n columns. And the mechanics of matrix vector multiplication say when we take A and multiply by x, what we're really doing is we're taking a linear combination of the columns of A using the coordinates inside of the vector x as the scalars. And when we do that matrix vector multiplication, we produce a new vector b, and b lives in Rm, which is the number of rows of A. So we take A, which has m rows and n columns. We multiply by a vector x, which has to have n coordinates. And when we do this, we produce a new vector that has m coordinates. So the idea here is that when we say we can view A as some sort of machine that has vector inputs and vector outputs, the inputs into A are vectors whose number of coordinates is the same as the number of columns of the matrix, and the outputs are new vectors, and the number of coordinates of these new vectors is the same as the number of rows. So this is a surprisingly useful idea and will motivate a lot of the concepts that we build throughout the course. And I want to sort of conclude this first lecture with a bit of notation that elegantly communicates this idea. So when we say that A has m rows and n columns, the typical way to say that is just A is m by n. But this perspective on matrix vector multiplication, which says that matrices have vectors as inputs and vectors as outputs, can be more elegantly written as writing A above an arrow, indicating between Rn and Rm, indicating that A will accept vectors from Rn as inputs and produce vectors from Rm as outputs. And this looks like maybe like a complicated thing, but it's no more complicated than simply saying that A is m by n. So if someone writes A over an arrow from Rn to Rm, all they're communicating is that A has m rows and n columns. And this idea will pop up again, and again throughout the course. So it's worth really sitting down and working through some examples to sort of digest this perspective. So that concludes our first lecture. We've learned a lot about some of the adjectives that describe matrices and vectors. We've learned a little bit about a few operations that manipulate matrices and vectors. And all of this was sort of designed so that we can understand this last slide here. To take a matrix and multiply by a vector is to create a linear combination of the columns of that matrix where we use the scalars inside of the vector we're multiplying by to create that linear combination.